Previously, we've looked at determining the percent composition of all the elements in a compound. What percent of the mass comes from a particular element in a compound? Now we're going to kind of do the opposite. If I was given the percent composition of a particular compound, could I go backwards and figure out its formula? That formula is going to be called an empirical formula. An empirical formula really does give the lowest whole number ratio of atoms in a compound. And so I could have something like H2O2, and that's a legit formula for hydrogen peroxide, but this would be called a molecular formula. Molecular formula. And we'll deal with those later on. Molecular formulas give what I kind of think of as more of a true ratio. Especially when you get to some of those covalent compounds, sometimes there really are 2 hydrogen and 2 oxygen. Sometimes there really are 8 carbon and 16 hydrogen. Sometimes with covalence, we just get really big molecules. And the ratio might not always be the simplest ratio. It's just a really big molecule, and maybe there really are 8 carbons and 16 hydrogens, and that's totally fine. We call that a molecular formula. It's more like the true ratio. It's often reserved for the covalent compounds. An empirical formula is the simplest or the lowest whole number ratio. And so here, if I had a 2-to-2 ratio, I could simplify that to a ratio of 1-to-1. That would be called an empirical formula. An empirical formula. And this would be like the lowest ratio. Whole number ratio, because we can't have like half an atom or something like that. The lowest ratio of elements. And so again, another example might be something like that C8H16. That might be the real structure of a big molecule. But I could also simplify that, and its lowest ratio would be like CH2. Now, there could be lots of carbon-hydrogen compounds that have the same empirical formula. I mean, I could have C8H16. I could have C2H4, C3H6, C5H10, and so on. Especially with covalence, we can just have big molecules, and we can have different numbers of carbon and hydrogen, but these might all simplify to the same empirical formula. And so they kind of say in the middle here that an empirical formula may or may not be the same as the molecular formula, which gives the actual number of atoms in the atom, or in the molecule, like the true ratio, the actual ratio. We're going to focus on the empirical formulas, which are often what we think of in reference to ionic compounds. Ionics always exist as that simplest ratio, the simplest repeating pattern in the crystal. I would never leave an ionic formula with a ratio of like 2-to-2. We would simplify that to a 1-to-1 ratio to show the simplest repeating pattern of the crystal. Now, sometimes covalents are empirical formulas, and sometimes they're bigger ratios, and they would exist as a molecular formula. Here's a good roadmap that shows you the type of data we'll be given and how to use that data then to calculate the formula. So in the last section, we had the formula, we knew what the compound was, and we were trying to figure out the percent composition. Now it's opposite. You would be given the percent composition and have to figure out the formula. And so here's step 1. Step 1 is to assume that you have a 100-gram sample. Because if I had 100 grams and 6% of it was hydrogen, then that's like saying 6 grams of hydrogen. I can take that percentage as a decimal. So 6%, flip your decimal spot 2 places to the left. That's like 0.06. Multiply that by your 100-gram sample. That should give me 6 grams of hydrogen. Do the same with your oxygen. 94% oxygen by mass. Assuming I had a 100-gram sample, that would be 94 grams of oxygen. Now, in reality, you could assume whatever mass sample you want, but it's just really easy if you pick a 100-gram sample, because then if 6% of it is hydrogen, that's 6 grams of hydrogen. If 94% is oxygen, you've got 94 grams of oxygen. Otherwise, let's say you assume that you have a 500-gram sample. Well, cool, but then you're going to have to multiply like 6% times 500 grams to get the mass of hydrogen and the mass of oxygen in your sample, which would put me right here. Now I've got 6 grams of hydrogen and 94 grams of oxygen. Now, if I know this compound is hydrogen and oxygen, I know the formula is going to be like H something O something. I'm looking for those subscripts that tell me the ratio of atoms, how many atoms of hydrogen to how many atoms of oxygen. So I want to get those grams into a unit that would represent a number of particles. I mean, the ratio in a formula is not a ratio of grams. When a hydrogen peroxide is listed as H2O2, it doesn't mean that there's 2 grams of hydrogen and 2 grams of oxygen. Those little subscript 2's are a ratio of atoms. How many atoms of hydrogen? How many atoms of oxygen? So a unit that represents an amount of atoms is the mole. And so if I've got grams, I've got 6 grams of hydrogen, 94 grams of oxygen, I can change grams into moles. That's step 2. Once you've got those percentages into masses in grams, we can convert grams to moles. So all we have to do then is set up that little ratio. We've done that before. We want to cancel grams, so that goes on the bottom. And that 1 gram of hydrogen, the 16 grams of oxygen, that's the molar mass. That's off the periodic table. Then I get those grams into moles. Awesome. Now from there, we want the simplest whole number ratio. And like maybe 6 is a beautiful whole number, and maybe my moles of oxygen come out to be about 5.88. Usually, I like to leave about 2 decimal spots in my molar masses. And then I like to leave about 2 decimal spots in my moles, just to make sure that I'm not rounding too heavily. So yeah, I mean, I've got 6 moles of hydrogen, 5.88 moles of oxygen. It's really close to a ratio of 6 to 6. But if you're not sure, you're like, oh gosh, it's not exactly a whole number ratio, or maybe you just get some really wacky numbers of moles and you're like, I've got no clue what this ratio would be. In comes step 3. Try dividing each by the smaller number of moles. And so here the smaller moles would be the 5.88. Divide both of them by 5.88, whatever one is smaller. And that should give us our simplest whole number ratio. So now I get a ratio that's like 1.02 hydrogen to 1 oxygen. And that's close enough to a whole number ratio. And so then that's step 4. As now we can write our empirical formula. This ratio of moles becomes our subscripts in the formula. So yeah, if you've got 1.02, that's close enough to round to 1. So the 1-to-1 ratio then would just become HO. That's my empirical formula, my simplest ratio, my lowest ratio of elements. It may not always be the true ratio, but here we're just going to focus on getting the simple ratio, the empirical formula. Oh my gosh, that seems like a lot of steps. It seems like a lot of work, right? It's going to be great. It's going to be totally fine. Here's just kind of another question that gets the point across, like what is an empirical formula versus a molecular formula? It says acetylene, C2H2, is a flammable gas used in welders' torches. It very much is. Styrene, C8H8, is used in like polystyrene, like packing peanuts and different forms of like plastics. What is the empirical formula for each? Okay, so empirical formula just means the simplest ratio or the lowest ratio. So if I've got C2H2, well, I could simplify that. C8H8, they're actually going to be the same. I could simplify those just both down to a ratio of 1 to 1. They have the same empirical formula. Describe why the empirical formula might be useful in the lab setting, but not useful for predicting the properties and or functions of a material. Well, I mean, the empirical formula is fine. It gives me the simplest ratio, the lowest ratio, but then I can assume that there could be other versions of this formula, especially when it's covalent, like these guys. These are both non-metals. And so, yeah, we can string together 2 carbons, 3, 4, 5, 6, 7, 8, 9, 10. We can string hundreds of carbons together. And so this empirical formula might help me predict then, like, if I had 5 carbons and I knew that the compound had the same empirical formula, well, I could predict then that it would have 5 hydrogen. You could predict the formulas. Now, if I had a compound and I knew that its empirical formula was like maybe something like C2H3, that's an empirical formula. That's a simple ratio. It's the lowest ratio. I can't simplify a 2 and a 3. Well, how might that be useful? Let's say I had a compound and I knew that it had the same empirical formula, but it had, oh, I don't know, maybe 4 carbons. Well, then I could still predict the amount of hydrogen. If the same empirical formula applies, I would have 3 times as many hydrogens. I should have 12. So there are some times when knowing the empirical formula is kind of handy, but obviously it's not great for trying to predict the properties. If I just knew that I had an empirical formula of CH, and I know then that there's lots of different versions of that formula, they're all going to have different properties. That's the law of constant composition that just says, in order to have a given set of properties, you have to have the same composition, which would mean the same elements in the same ratios. And so if it's not the exact same ratio, I mean 1 to 1, 5 to 5, it's not the exact same ratio, I'm going to have different properties then.